All right, so we're going to be doing lesson 4.5, solving trig equations. So here we have an example of the kind of thing that we're going to be looking for. Solve sine 2 theta is equal to 1 over 2. So what is this asking us to do? Again, I'm kind of just looking at this part right here for right now. This is asking us to find the angle. So solve for our variables, find the angle that satisfies this, that if I multiply the angle by 2, I get a sine ratio of 1/2. The second part over here is a restriction on the range of our solutions. So we should find all solutions that fall in this range between 0 and 2 pi, including 0, not including 2 pi. So we're going to be examining the entire unit circle, and we're going to find all of those solutions. Sometimes that can be a little bit tricky, and we'll kind of see some times where that's the case, where finding all of the solutions will require us to do a little bit more than what maybe seems obvious. How do we find the answer? Well, part of that is just going to be using the unit circle. Kind of depends on the equation that we're looking at, but a vast the actual solution part is going to be heavily reliant on the unit circle. Okay, so let's go ahead and look at this. So some general guidelines here. When we're solving the trig equations, we're going to try to find all solutions that fall between 0 and 2 pi. Again, in some cases, which we will look at, this may be challenging. We will have to go a step beyond just finding the angles that are obvious. We're going to have to go one extra step beyond that. There are going to be multiple solutions, almost always. Sometimes 3, 4, 5, or more, depending on the degree of the equation and some other factors. Some things we're going to need to know how to use and be able to do when we're solving these, making sure we're pretty fluent with the unit circle. We know where to find certain ratios on the unit circle. Using our calculator, sometimes it may be necessary to use the inverse trig functions to approximate some solutions. Substitutions, we're going to be making substitutions sometimes to help us solve these equations a bit easier. Working with the identities, so Pythagorean identities, quotient identities, reciprocal identities, all those things may need to be applied to sort of change our equation to a more solvable form. And factoring, all kinds of different factoring may come up. We'll look at a few common ones here today. All right, so we're going to kind of go through a few different types. These are roughly grouped this way. Obviously, there are some small differences here and there between kind of all these different types, but these are what we're looking at. Mostly in part one, we're going to be looking at these two here. Kind of ones that are more straight away, we're just jumping into solving using the unit circle, and a little bit of substitution in there too, and then using calculators to approximate solutions. So those are going to be the two things we look at in part one here. Okay, so we're going to go ahead and solve this using the unit circle. All right, so here's our equation. Sine of theta is equal to negative root 3 over 2. Very straightforward. We're trying to find the angle theta that has a sine ratio of negative root 3 over 2. This is a problem. Nothing not going on inside the sine function, nothing going on the outside. We're ready to solve. We're ready to look at our unit circle and solve. So we want to know what angles have a sine ratio of negative root 3 over 2. On our unit circle, the sine ratios are the y coordinates. So we can find, oops, that's an x coordinate. We can find the y coordinates that have negative root 3 over 2 right here and here. So our two solutions are going to be theta is equal to 4 pi over 3 and 5 pi over 3. Those are our two solutions. Again, finding those angles right there. For sine, you're going to notice that our solutions are kind of symmetrical across the y-axis here. For cosine equations, they'll be symmetrical across the x-axis. In this case, this is all we have to do. We do know that there are technically an infinite number of solutions here for this, right? If we take this angle here and we just add 2 pi to it, so 4 pi over 3 plus 2 pi, that would be another angle. That would be a solution, obviously coterminal with this same angle. So we would just go full rotation, and then we would go 4 pi over 3. So this angle would be coterminal with it, wouldn't be unique at all. But sometimes we need to investigate that in some cases. to see whether that may be a unique angle. Anyway, these are our two solutions. Very, very straightforward problem. Okay, let's go ahead and move forward. See one that's maybe a little less straightforward. All right, here we go. Cosine of 3 theta is equal to 1/2. This one's a little bit funkier because we have something going on inside of our trig function. What we're going to do before we go to the unit circle is we're going to make a substitution. We're going to create kind of an intermediate variable here. I'm going to use the variable z. So let z equal 3 theta. And we're going to use that to rewrite our equation. Cosine z equals 1/2. Now here, this equation is much simpler. Nothing really going on inside of our cosine function anymore. We made that substitution so that we just have this singular variable. Now we can look at our unit circle. We can find where on the unit circle, what angles have a cosine ratio of 1/2. Remember, cosine is the x-coordinate. So we have one right here, pi over 3. And we have this one right here, 5 pi over 3. Those are the two angles that satisfy the variable z. So these are solutions for z. Pi over 3 and z equals 5 pi over 3. But we are not done. Those are not solutions for theta. And we have to be careful. In this case, once we have modified this argument for our trig function, there may be more solutions hidden in here, and we have to be a bit careful with this. So I'm going to unsubstitute, but I'm also going to consider one aspect here. We know that there are an infinite number of solutions that are coterminal with this, right? So if we add any multiple of 2 pi, we'll call it 2 pi times n to this, where n would have to be an integer, a whole number, a positive or negative whole number, that these angles should be coterminal with those. Let's get back to that in just a second. Now let's unsubstitute it. We'll do 3 pi is equal to pi over 3 plus some multiple of 2 pi. We'll call it 2 pi n. And then we have z is equal to 5 pi over 3 plus some multiple of 2 pi. Sorry. Oh, I don't know why I wrote that as z again. Remember, we were unsubstituting. This is supposed to be 3 theta. All right, things are getting a little cramped here. Let me move some things out of the way. Maybe we'll do this. Okay, we're solving for theta, right? So to solve for theta, we need to simply divide both sides by 3. Okay, so we got theta is equal to pi over 3 plus 2 pi over 3 times n. That's not pi over 3. Why did I say that? Pi over 9. Pi over 9, let me divide that, obviously. 2 pi over 3n. So this is a little different now. This is saying pi over 9 plus some multiple of 2 pi over 3. We might have some more angles that fall inside of the range 0 to 2 pi to satisfy this. So let's go ahead and do this last one again. Divide everything by 3. We end up with theta equals 5 pi over 9. Dividing by 3 makes that 9. Plus 2 pi over 3 times n. Plus some multiple of 2 pi over 3. Interesting. Again, we may end up with some angles that fall inside of this range. So we gotta do some investigating here. I am going to create myself a little table. So we have our base solution. Our two base solutions are pi over 9 and 5 pi over 9. We got those from just simply taking the angles we found on the unit circle, substituting in the 3 theta, dividing by 3, whatever, get these solutions, right? These are solutions. But we're saying if we add some multiple of 2 pi over 3, which is a small period, right? Because this right here, this is technically a b value, which is actually shrinking the period. This function is oscillating faster within that standard range of 2 pi. So there may be other angles that satisfy our solution. So these are the ones we need to find. These are the ones that are very straightforward. You got to be able to find those. These next ones are going to be the tricky ones. So I need to add 2 pi over 3 to that. 2 pi over 3, let's think about that in terms of 2 pi over 3. We multiply that by 3. That is 6 pi over 9. So if I add 6 pi over 9, we end up with an angle of 7 pi over 9. That's different than both of those, but this angle is supposed to work. Let's add another multiple of that. So add another 6, that would be 13 pi over 9. That's another angle. That's different than all these two. This still is less than 2 pi. And let's add another one, add another 6 pi over 9. That would be 19 pi over 9. Okay, this answer I'm going to reject because this answer is greater than 2 pi. Greater than 2 pi. 2 pi, remember, is something like 18 pi over 9. So it's greater than that. So this answer we're going to reject. Ooh, boy, I kind of made a mistake there. Let's try that again. Okay, that'll do. Okay, so that answer we're gonna reject. So because we only want to find solutions that fall in the range of 0 to 2 pi. But all these answers are good. Okay, so let's add 6 pi over 9 to this one. That's going to be 11 pi over 9. That definitely falls in this range, right? That's between 0 and 2 pi, and that's different than all these other ones. Let's add another 6 pi over 9, which makes this 17 pi over 9. That's still good. That's still less than 2 pi. Remember, 2 pi is equal to 18 pi over 9. So it's still falling within our range. It's less than 18 pi over 9. Can't add any more, though. Any more, I would actually go over. So we have found a lot of solutions. We found 6 solutions. All of this is technically correct. For what we're doing right now, you know, if you end up with only these solutions, I'm going to be okay with that. But technically, all of these solutions are good too. Let's examine this graphically. Let's look at the graphs of this and just make sure that we can kind of understand how this is going on. So I'm gonna leave this page. We'll clear all this stuff off. And let's take a look at the Desmos graph. This is another way that we can examine the solutions to these problems. So cosine 3x. Okay, so here's our equation. And that was supposed to equal 1/2. So we're going to create a line of y equals 1/2. Now, you know, for these things, we want to make our scaling along our y-axis something nice. So let's zoom way in. Let's only go from 0 to 2 pi. 2 pi at the end, 0. Okay. So we can see just by looking at it, right? There are these. How many is that? 1, 2, 3, 4, 5, 6 solutions. 6 solutions that satisfy that equation in our standard range of 0 to 2 pi. When you're solving these, this process that we're going through right now of looking at multiples of 2 pi, adding on and all that, it's only going to happen when we have something in here that changes the period of our function. If the period of our function is not being changed, then we don't need to worry about what we're doing in here. But when it is, we do need to. But look, you can see right here, look, all Desmos finds all the solutions. So once you find the first two algebraically and using your unit circle, if you want to examine Desmos to help you find these other ones, it's fine with me. I think that's good for right now. But you should know that there are all these solutions out there. and how to find them there on Desmos. Okay, clear this off. We'll maybe use that again, so I'm going to leave that open. Okay, let's go ahead and go back to the present mode. Okay, same idea, similar idea here. We have tangent. Tangent of 2 theta minus pi over 3 is equal to -1. Okay, you know, we could graph this on Desmos, and I certainly will eventually here, but let's go ahead and talk about the algebraic methods that are necessary here. So I'm going to start with that substitution. I'm going to be replacing the argument inside of my trig function. So I'm going to create a new variable. I'm going to say let z equal to pi, or 2 theta minus pi over 3. So you can just replace that whole thing, keep it kind of simple. Tangent of z equals -1. So now we can look and find where on the unit circle do we have a tangent value of -1. I went ahead and searched up this handy tangent unit circle with tangent values there. And you can see right here, 3 pi over 4, we have a tangent value of -1. 7 pi over 4, we have a tangent value of -1. So those are going to be our two solutions for z. Z equals 3 pi over 4, and z equals 7 pi over 4. Now, because we have modified the period of this function a little bit, got to be careful. There are going to be other angles that fall within 0 to 2 pi that satisfy this. These aren't going to be the only ones. These are the easy ones to find. These are the ones that come up right away, but there will be more. So knowing that the period of tangent is pi, so plus pi times some multiple of n, plus pi times some multiple of n. We have to solve. We have to unsubstitute. So we replace z with this. We say let 2 theta minus pi over 3 equal 3 pi over 4 plus pi n. You can see how this is going to get a little messy, but that's okay. We would add pi over 3 to this. So we'd add pi over 3. We have an uncommon denominator. Well, we don't have a common denominator anymore. Common denominator would be 12. So 3 pi over 4 is going to be 9 pi over 12. And pi over 3 is going to be 4 pi over 12. So adding those together, we're going to get 13 pi over 12 plus pi n equals 2 pi. One more step here, right? We're dividing by 2, dividing everything by 2. Okay, I'm kind of doing this whole process here, but you can see it's getting a little bit ridiculous. I'm going to jump to Desmos rather than go through this whole nonsense again, but I'm just showing you what's happening. Divide this by 2, I need to distribute. I end up with 13 pi over 24 plus some multiple of pi over 2. So all of my solutions are going to fall in this form or a similar form based on this angle right here. Again, not going to go through this again, but that's what will happen. So let's go ahead and check this out on Desmos instead. So these are the two solutions you need to come up with algebraically. We're going to examine the other two on Desmos. So this is my equation. We had tangent 2x minus pi over 3. Might have misspoken on that. Is it minus or is it plus? Boy, oh boy. Okay. It's minus. Okay, good. We're looking for when it's equal to -1. -1. And we're looking for all the solutions that fall between 0 and 2 pi. So that's what I have here, between 0 and 2 pi. Okay, great. Yeah, I can find all my solutions right here. So here are all of my solutions. Pi over 24. Pi over 24. Got that one right there. We got 13 pi over 24. We saw that number showing up there before. We got 25 pi over 24, got that one right there. We got 37 pi over 24, got that one right there. So this one actually had 4 solutions. I got rid of them somehow, but let me click them back. When we run into something a little bit more difficult like this, I definitely think the graphical approach is an appropriate response and way to find our solution. Okay. Let's go ahead and move forward. Okay, and then we have this problem. Secant of theta is equal to 4. Some people don't like this because it's secant, you know, why would you do this? Let's turn it in terms of cosine. So if secant is 4, that means that the cosine is going to be the reciprocal. Cosine is 1/4. So turning it into cosine maybe makes it a little bit easier. Remember, cosine on the unit circle is the x-coordinate. So if we have a unit circle, I'll just kind of sketch something out here. Here's a unit circle, at least approximately a unit circle. Let's go ahead and move this around. Yeah, we'll just call this our unit circle. So, you know, radius of 1 and 1/4. The cosine value of 1/4 means, let's see, this is a half. This right here would be 1/4. 1/4 means we're looking for spots on our unit circle, like here and here. These are basically the angles that we would be examining. These are the angles that would give us this solution. It would have a cosine value of 1/4. We're going between 0 and 2 pi, so we would get this solution, whatever this angle is, and we would get this solution, whatever this angle is. So this would be our second solution. Solution 1, solution 2. Well, we need to figure those out. How can we figure those out? That's not on, this ratio is not on the unit circle. I can't just look up 1/4, it's not there. So what do I need to do? I need to use inverse trig. So if cosine of theta is 1/4, then I can use inverse trigonometry. I can take the inverse cosine of both sides here and end up that our angle is equal to the inverse cosine of 1/4. This is a situation where I have to use my calculator to estimate. When I'm using my calculator to estimate, I want to keep my answer in terms of radians. So I'm going to do that. Inverse cosine of 1/4. I found that this angle is approximately, this first one here, let's do it in blue. This first angle here is approximately 1.32 radians. So that's one of my solutions here, 1.32 radians. I need to know what this one is. This requires a little bit of thinking. We know that our solutions are symmetrical across this x-axis with cosine, right? So if this angle here is 1.32, this angle right here is also going to be 1.32 radians in the negative direction. But that way, if we're just measuring the angle there, that angle is 1.32. Well, the way I can find this one, our second solution here, is I can take a full circle, 2 pi, minus this piece right here, which we just said is approximately 1.32 radians. And this is going to be our second solution. So 2 pi minus 1.32. I'm going to go ahead and get a decimal approximation for that again. When in doubt, I'm just going to go 2 decimal places, so 4.96. So my second solution is approximately 4.96 radians. So let's go ahead and check these. Let's make sure that these solutions actually work. Again, these are the 2 solutions that we got. Make sure that they work. Let's well, let's not plug it into secant, but let's plug it into cosine. We'll plug it in right here. So we will do cosine of 1.32. Just make sure it's really close to 1/4. We're close. 0.248. 1/4 would be 0.25. So actually, that's pretty good. It's probably as close as we can get with 2 decimal places. Let's try the other one. Cosine of 4.96. Oh, yep. Just as close, pretty close. 0.245. Not quite as close, but pretty close to 1/4. So those solutions are great. We're gonna go ahead and go with those. And those are between 0 and 2 pi, the only solutions for that, because we didn't change the period of this function at all. Okay. Let's do one more of those. We got cotangent is equal to -2. Again, when it's in one of these functions, I prefer to write it in terms of either sine or cosine or tangent. So cotangent and tangent are reciprocals. So I can change this to a tangent equation. The tangent would be the reciprocal of this, which is -1/2. Okay, this one's not so obvious. Like, where would this fall? Where is tangent negative? Tangent is going to be negative either in quadrant 4 or quadrant 2 here. The reason being is because in this quadrant we would have a -x and a positive y. So when we do our ratio for tangent, y over x, we get a positive divided by a negative, so it's negative. And in this quadrant, we'd have a positive x and a negative y. So again, negative divided by positive, we'd get a negative. So we know we're going to fall, our two solutions are going to fall in these quadrants. Being that it's y over x, we know that the x component is going to be a bit long, going to be twice as long. We could even set up a little right triangle situation here where it's 2 and -1, right? That's one of our situations here in terms of a right triangle. And then the other one would just be exactly symmetrical over here. Same idea. 1 and -2. Negative for the x this time because we're going that way. Well, our two solutions, again, we're going to have two solutions here. One of them is going to be this angle right here. And the other one's going to be this angle right here. We need to find those two angles for our solutions. Those are going to be the angles that are between 0 and 2 pi. Well, we can kind of find a solution for this using inverse tangent. Inverse tangent. So if I rewrite this in terms of inverse tangent, I'd get that theta is equal to tangent inverse of -1/2. So let me just do that and see what happens. Tangent inverse of -1/2. All right, here's what I get. I get -0.46. That's making me think. That's making me think. So I get -0.46, 0.46. What angle is that? It's not a positive angle, it's a negative angle. That's this angle. That's because inverse tangent has a range between -π/2 and +π/2. So because I used inverse tangent to solve this equation, it did not give me a solution that fell between 0 and 2 pi. It gave me this angle here, right? Because inverse tangent, the range, when I have an angle down here, it's going to give me a negative angle, and it gave me -0.46. That's not the solution I want to express, but it certainly is a solution. This is fine. It just doesn't fall in the proper range. So I need to figure out both of these things, right? Using old geometry here, I do know that these two angles would be considered vertical angles. So this one over here would be 0.46 also. So I can kind of use a little problem solving to figure some things out. So this first angle right here is going to be 0.46 shy of pi. So it's going to be pi minus 0.46. It's going to be this angle right here. And this angle is going to be 0.46 shy of 2 pi, shy of a full rotation. So I can find my two solutions here by simply doing this. So pi minus 0.46. I get my first solution of approximately 2.68 radians. These measurements are in radians. I've kept everything in radians here. And 2 pi minus 0.46. So I get 5.82 radians, approximately. Again, when we have equations like this, the best that we can really do is decimal approximations like this. I'm going to go ahead and go to Desmos, kind of have a brief conversation about these two, and then move on. So let's go ahead and go back. Let's delete some stuff here. We had secant x. So y equals secant x, y equals 4. So we could have approximated those solutions that we came up with before, right? So we came up with 1.32 as one of our solutions and 4.96. Looks like Desmos actually rounded this up a bit, but notice how I was able to find that graphical solution way faster than all that stuff that I did. For using a calculator, might as well use a really good one, right? Let's go ahead and try the same thing. We had cotangent x, and we were looking for when it equals -2, y equals -2. We found those solutions too. Those are the solutions that we found. So 2.68 around and 5.82. Again, if we're going to use a calculator to find the solutions, why not just use a really good calculator? So Desmos is very powerful in these situations where you have to approximate solutions, and I would definitely encourage that. Anyway, I'm going to go ahead and stop this part, and we'll pick up the rest in part 2.